finishing lesson 2, bottom of page 4 of your lecture notes. If we're looking at the graph, you see I've made the graph for you and actually did the math for you because that wouldn't be expected. It's just to show a point on this. We see that the rate, our concentration, we doubled it. We ran an experiment of this and started with 0.350 molar nitrogen dioxide, and then the next experiment we jumped that up to 0.7 molar. So it was doubled. And graphically we see if we do the initial rate that the rate tripled. All right, so that leads us back to what we were talking about in the collision theory, that one of the ways of speeding up a reaction is to increase the amount of reactants we have. So there's a definite relationship, and we'll write this in a general sense. There's a definite relationship between rate and initial concentration. All right? Just to give you a heads up on rate, it's a molarity per second, right? But it can be written different ways. For instance, you can just see to the -1 with the S. Or you can see moles times liters -1 times second -1, because molarity is moles over liters, right? All right. And then obviously, if this were partial pressure, you would have the unit of pressure over time. And again, they can do the same thing with that S -1. So I don't want you to freak out when you see these exponent in the units. All right? Okay, and change always means final minus initial. Okay. Rate itself will always be positive. However, if we're looking at it with rate equations as the disappearance of a reactant, then we put a negative sign on it. Okay, so that finishes up lesson 2. Now we're going to get on to something different. And in your notes we see the rate equation, remember these words, is when we looked at the rate from the perspective of one of the reactants disappearing or one of the products appearing, and how we made an equivalence of that. Remember, if we always start, anything we're doing always starts out this way, rate equals something, all right? And then we could make equivalence by switching those coefficients. And now we're going to look at something different called a rate law. And the rate law says, instead of just looking at one thing individually, what if we are looking how the interaction of the two reactants are of, if we have more than two, or if we have just one, but the perspective of saying, what is the rate of this whole thing collectively? Instead of just saying, let's look at the rate of one thing as reactants disappearing or a product is appearing. It's saying the interaction of these two. How does it affect the overall rate of the whole thing? And that is called a rate law. That's different than a rate equation. All right? It is also, a rate law never looks at the balanced chemical equation. Okay? This is key. One of these very well-tested facts about how you get a rate law. You do not get a rate law from a balanced chemical equation. You have to experimentally determine a rate law. All right? And so I'm going to show you the differences, how it's written and how you say it, and then we'll get into it. Because when you first see it, it's going to be confusing, but we'll walk through it. Okay, So here's an equation. You've got this particular reaction, H2 plus I2 going to 2HI. All right. Those are all gases, by the way. Remember, I told you in your lecture notes, if it doesn't say, just assume it's a gas. Okay, and we know that if we wrote a rate equation, rate equals, and we could say, we could look at it from the perspective of the change in the H over time, or we could say the change in I over time, or, and this is where we look at the Balanced chemical equation, half the rate of the HI over time. That would be our rate equation. Our rate law for the same equation is going to look something like this, and it's always going to start out rate equals, okay? Rate equals, and then we have this lowercase k, this is called a rate constant, we'll get into that a little later, times h2 to some exponent, I2 to some exponent. All right? This would be a rate law for this equation. This would be saying how these two react, what does it do to the speed? A rate equation says how much, what is the rate that an individual species is disappearing or appearing, all right? So x and y, these exponents, are experimentally determined. All right, they are not, do not get these from the balanced chemical equation. I can't emphasize that enough. Put a star by that or whatever. That is tested. All right, they are not, what do I want to say grammatically there? They are not gotten. They are not.
You're not found.
Found, okay, from the balanced chemical equation. All right, so we got to experimentally determine these. All right, now let's talk about how you say this. First of all, we discuss order of reactants. And notice that this is all, a rate law is from the reactants. You don't have to worry about the products, right? It's just the reactants. The order of the reactants, the order of the reaction. And then we have, let's just say for the sake of argument that x equals 1 and y equals 2. So this is what we would say. We would say H, well, no, just don't have to put concentration. We would say hydrogen is first order because it has an exponent of 1. So what do you suppose iodine would be? Second order, yeah, okay. Iodine is second order. All right, okay, so now we know the order of the reactants. How do we get the order of the reactants? It's just the exponent. That is experimentally determined. And we'll show you how to experimentally determine that in just a minute. All right, but notice they don't necessarily match the coefficients. These are experimentally determined. They're not from can they match the balanced chemical equation? Yes, but if they do, it's a coincidence or something else is going on that we'll discuss later. All right? And this is how you say it. Whatever that number is its order. Now, to say the reaction then, as a whole, you add up those exponents. All right, so 1 plus 2 equals 3. So this is a third order reaction. So, order of the reactants, put it together, what is the order of the entire reaction? All right, remember we ended lesson 2 by saying there seems to be a relationship between rate and initial concentration. Okay, a relationship isn't a mathematical equation, is it? It's saying, boy, it seems to be they're related. Okay, this is the function of this K. It turns a relationship into a mathematical equation. Okay, so it's almost a perfect mathematical relationship. It's off by a little bit. So we throw in a constant. All right, so K is our rate constant. And the units are hugely important. And different for different orders. All right? So you can tell by the units of a rate constant if it's a first, second, third order reaction. Because they'll each have a distinct, because it's mathematically the way it cancels. Right? Remember in equilibrium we said let's not worry about the units because of the way we set up those coefficients and everything, you know, trying to say molarity cubed over whatever would just be ridiculous. But in kinetics, it's the same thing, only this time we say it's not ridiculous, we're going to make you do it, all right? So, because it's a little easier to figure out. And once again, we said when we start with initial, it has that subscript. If we had partial pressure, it would look like that. Okay? And the rate law is written, those concentrations are initial. Because we said we're always going to use initial. Because that's when it goes the fastest, that's when we have the most, that's when we are sure that it's going 100% towards the production of products. And then it gives us a good equivalent comparison between other reactions. If we all have this standard point of starting. Let's talk about the units, just scribble this in, because let's see how that would work. Okay, rate, we just made this up for that equation with what we say, H to the 1, iodine to the 2, right? We said this is first order with respect to hydrogen. I like to say that. It's not imperative you do, but it is first order with respect to hydrogen, it is second order with respect to iodine, and it is third order overall. All right? Now, to show you how that plays out with units, let's look at the units, okay? Rate is always molarity per second, correct? If it were partial pressures, it would be partial pressure per second. All right, so now we have K, and this is molarity per second to the 1, correct? And this is molarity per second squared, right? Okay. So this is molarity over seconds, and technically this would be cubed. Does that make sense? All right. Now, if we're solving for K, all right, then our rate divided by I'm sorry, this is just molarity. Huh. Knew that second was weird. All right. That's not rate, that's just concentration, is it? Very sorry about that. All right, so we have to say, how is that going to cancel? Well, obviously, we're going to lose that m, and this one will reduce down to 2, correct? So the units for a third order reaction then are going to be molarity to the -2 and look like that. And those would be unique to a third order reaction. You could look at those units and say, ah, it's a third order reaction. All right? Let's say you had a first order reaction. Let's just try this. Okay? Instead of this, let's just say, well, let's just say this is 0 order. Can you have 0 order? Yeah. Right. You can have fractional orders. You can go nuts. Right? Okay, so we would say this is first order with respect to hydrogen. This is 0 order with respect to iodine. So it is 1 plus 0. It is first order reaction overall. Right? That's worth 2 or 3 points on the AP exam. Right? And you'll notice that in your homework, you know. What is the order of each reactant? 1 point for each, you know, order. What is the overall order? 1 point for the correct, you know, you don't want to lose this. And then what is K with the correct units? It's always say that. Look on your homework. What is the K with the correct units? Because this is where. So now let's redo this. All right, with just units. Okay, now we have rate is molarity per second equals K, and this would be molarity. And then we have that, correct? Right, so now let's solve for K. Well, in this case, it's molarity per second divided by molarity equals K. Well, these are going to cancel, aren't they? So the units of K for a first order reaction, okay? And if you saw those units, you would know that it is unique to a first order reaction. And that's how this shows up on the AP, on the multiple choice. They'll say this reaction, they'll give you a reaction, has a rate law that looks like this. What would be the correct value for K? And then they'll show you with the units different. And then you gotta say, oh, that's third order reaction, so my units need to be this. It's, you know, choice C.
So you can generally just think about it as whatever your order is, like -1, and then just have a negative.
Very good. Yeah. Yeah. Your K will always have 1 less molarity than your order. All right. Now there's one time if it's a 0 order reaction, then K equals the rate. But just, you know, walk through it so you don't make a stupid mistake, because you're not getting out of kinetics without writing the correct units of your K. And that's an easy point. All right? And be careful of sig figs, because you could go nuts with these. You know, 5.32158 times, you know. All right, so that is how we say these things. All right? Now, let's look through how we would actually experimentally determine. All right? So what we would need, because this is once again a procedure, how do I set up a kinetics experiment? Okay, so I have this reaction. Now, how do I monitor change? Well, a lot of times, a reaction will change color. So what you can do is start the reaction and put it in a spectrometer and look at the absorption over time. You can time it with a stopwatch and watch what happens to the absorption, because absorption is equal to concentration. Another thing we can do, and what we'll do next week, is look at the partial pressure. Well, actually, it'll just be a pressure. And it doesn't matter what you're looking, what pressure, what, that's not relevant. It's okay, you're going to look at, we're gonna set up a lab quest with little pressure sensor gauges, all right? And we're going to look at hydrogen peroxide decomposing, all right, with a catalyst, all right? And then what you're gonna do is it will produce oxygen gas. So what you're gonna do is relate the concentration of the hydrogen peroxide to the pressure that the oxygen forms, you know, and that's fine because that's just, you're just relating it to the rate of something, but you're looking at the reactants, all right? So what we would do is we would set up some different experiments, all right? Right, and then what we do is we would start with different molarities. And let me show you why some of these are the same. So what we're doing is we're recording data. We've said, I'm going to see how a change in my H concentration affects rate. All right, well, to isolate H, what do I have to do? I have to hold I constant, don't I? If I'm changing both of them, how will I know? All right, so what we do is we say, okay, I'm going to hold I constant, and I'm going to change the initial concentration of H, and then I'm just going to see what is the rate that is formed. What does it do to the rate? Okay, so what I noticed, so what you're doing is you are just physically making some concentrations, and then you're reacting them, and then you're watching what happens. That's it, all right? But what you're doing is you're determining what that initial concentration will be. And notice as we analyze this, so let's look at, we're going to keep the conditions same as we go through this. We'll keep the temperature the same. And why would we keep the temperature the same?
Another variable to add.
Yeah, because we know what happens to K with a temperature change. Yeah, yeah, that's back to any time, all right? In equilibrium, we said, you know, K is constant at a constant temperature. So the first thing we're gonna do is make sure that our temperature, you know, our conditions are the same. All right, and then we're going to vary the initial concentration of each reactant. All right, we're going to make sure that one concentration is held constant. And then we're just going to look at the effect on rate. All right. So what you'll be doing next week, let me write that one down. We got the decomposition of hydrogen peroxide using a catalyst, and we'll actually make a concentration of that catalyst, all right? And then it will decompose according to this, all right? And then what we're going to do is that we're going to vary the initial concentrations of these two and see the rate at which oxygen is produced, all right? So we'll time it and look at the change. Let's say initially we have, you know, no partial pressure, right? Well, it would be atmospheric pressure. And then we're going to add that catalyst, we're going to hit the stopwatch, and we're going to monitor that change in partial pressure. And then we're going to relate what happened to different concentrations and what happened to the gas. Do you have a point, or you look like you're about to?
Oh, sorry.
All right. Okay, so, but it's important here that we make sure if I'm looking at iodine, I'm holding the concentration of hydrogen constant. If I'm looking at hydrogen, I'm holding the concentration of iodine. And then I say, okay, if I hold this constant and this, I double the concentration, what happened to the rate? Wow, quadruple, right? If I hold this constant and I say what, double? Yeah, double it, what happened? Woo, yeah. Octupled. Okay? So that's it. That's how it's experimentally determined. And this is how you set up your experiment. Okay. Always think, this is, I say, a new emphasis on the exam is that you know how to design an experiment to find out. All right? And designing an experiment on this is really easy and straightforward. You just sometimes don't think about it. You're so caught up in the mathematics of it that, yeah,
is the fourth one needed?
no. Yeah, I see there. I do want to show you that you look for where was this one held constant. You know, you don't say the first and second weren't done, then this should have been the third. No, just look over your data. Now another thing is when you actually collect data, do you think you're going to get numbers that perfect?
No.
And just round. Okay, that's the thing with these problems. They'll set them up for you to where it's beautiful. It's, you know, wow, it doubled, you know. Ours, it 1.8, you know, I mean. So we'll just remember the difference between actually doing something and theoretically, yeah.
And these tables will only be to get the next step for like a question, right? We won't ever have questions where it's like, by how much did the rate change by?
Well, no, but what you'll do is you'll be given this data, and then you'll say determine the order of H, determine the order of I, what order reaction it is, what is your rate constant, and what are the units of your rate constant, okay? So that's where we're headed. So first of all, I want to show you how we experimentally determine, all right? This is what we would do, and this is what you guys will do next week after you watch 10 videos because of all the class time. Anyways, think of it. You had a whole bunch of snow days, right?
Not for this. We didn't ask for this.
We didn't.
We only somewhat signed up for this.
Okay, so now the fun part. Let's mathematically calculate it. Let's see how it works.
Let's involve numbers. Guys.
Yes, woohoo!
All right.
Cruz is finally saying yes, math. He's probably already figured out the math. Okay.
It's not a joke at this point. He actually did.
All right, so here I've given you, now after we do this one, you're going to see that you can now do the majority of your homework. I think most of your homework almost starts out with, here's some data, go for it. All right. Okay, so we're given this reaction on page, what page are we on? 7. All right. It says 2 nitrogen monoxides start with, react with 2 hydrogens to go to 1 nitrogen and 2 waters. And notice this is homogeneous. They're all the same phase, they're all gases. And we're not going to get our rate law from the balanced chemical equation. We're going to experimentally determine it by setting up a table and monitoring, changing concentrations and seeing how it affects the rate. Okay, so it says determine the reaction order for each of the reactants. So let's look at that. Okay, I am going to look at hydrogen. So to get hydrogen, I have to look at NO and say what experiments was the partial pressure of nitrogen monoxide held constant. And what experiments would that be? 1 and 2. Excellent. Okay, now I'm going to set up a ratio, all right? And the ratio, it will always be mathematically easier if you put the bigger number on top, all right? So don't say, but it went from 1 to 2, so it went 150 over 300. You don't want to do that. You just want to keep your ratios constant. So obviously we changed in experiment 1 to 2. We started with this partial pressure, and reduced it, or we could say we started with this, doubled it, doesn't matter. Okay, and then I'm gonna look at the rate. What happens to the rate? Well, the rate went from 1.34 to 0.66. All right? So this doubled and this doubled. All right? So what's the rate order? Well, you say 2 to what gets me 2?
What?
Yeah, all right. So you're going to get this number, and this is where you're going to get the order. You're going to say 2 to what factor gives me 2? Well, 1. X equals 1. So that means hydrogen is first order. Viola. That's what you do. And you're going to see from your free responses, if you can work through this, you're going to nail most of any kinetics. Okay? All right, now let's do the same thing with the other reactant. Now, I have to say, to get NO, when do I hold H constant? What experiments was H held constant?
3, 4.
Very good. All right, so now I'm going to look at NO. It went 300, 150, and what happened to the rate? 1.03 to 0.25. So this is 2. 2 to some exponent will get me 4. 2 to what gets me 4? 2. Yeah, all right? So Y equals 2. So what does that mean? Nitrogen monoxide is second order. All right, there's 1 point on free response. There's another point on free response. Okay, determine the overall order of the reaction. Well, 2 plus 1 equals 3. This is third order reaction. Think we can handle that? You will have your calculators on the free response.
We gotta make sure.
Yeah.
I gotta make sure.
Yeah.
If it's too simple, we gotta make sure.
Okay, now write the rate law for this reaction. And this is where sometimes students forget the rate equals. That's why I've been pounding into you. Everything starts out with rate equals. So the rate law for this, putting this together, would be rate equals some constant times the partial pressure of hydrogen times the partial pressure of nitrogen monoxide squared, right?
Does it matter which order they go in?
No. Once again, this is an equation. So let's look to answer your question. Does that matter? All right. Doesn't matter what order you're.
Oh boy.
Little kinetics humor there, yeah.
There we go. That's all we know.
Little. The emphasis is on little. Okay. Okay. Determine the rate constant for the reaction and include the units. All right. How do we get the rate constant? Well, you can take any experiment and just fill those values from the table into this equation. That's it. Okay? Because you know all these numbers from your table, going back to using your data. All right, so let's just look at experiment 1 because it's the first one there. And I'm going to place in, the rate is 0.66, what is that, millimeters of mercury per second is equal to K times the partial pressure in the first experiment is 150 millimeters mercury times, for NO it's 400 millimeters of mercury squared. And now I just do the math, right? Be careful on that. But you have your calculators. Once again, your life is saved. But so I'm going to, let's just take this step by step, 0.66 millimeters of mercury per second is equal to 2.4 times 10 to the 7th millimeters of mercury cubed times my K, right? With me so far? Then I divide 0.66 millimeters of mercury per second divided by 2.4 times 10 to the 7th millimeters of mercury cubed equals K. All right, that millimeter of mercury is going to cancel. One of those will cancel. So my units are 2.75 times 10 to the negative 8 millimeters of mercury to the negative 2 second to the negative 1. And if you don't get those units right, nothing you just did, because this will be worth 1 point. Sig figs, getting the math right and making sure those units. Units are everything. Everything. Shows up on the multiple choice by them just giving you a rate law and saying, you know, what would K be? And you're going, how the heck? I can't mathematically. It wasn't about math. It was just, can you recognize correct units? We good so far? Not that bad, is it? If you can do what we just said, you can probably get a 4 out of 5 on any kinetics free response. So that's why I've given you so many free response homeworks, because we're going to do this over and over and over until I get it. Muscle memory.
Perennials.
Because of perennial, yeah. All right.